$10,000 to go.
I hope
Yeah,
someone
they're
calls
gonna-
you.
Okay.
I'm gonna answer it.
Huh? So you see that? Alright, here you go. Polynomials and rational functions. We're going to continue talking about those, but today we're going to talk about them in regards to inequalities. Okay? What we've been doing with rational functions is just graphing, right? Finding x-intercepts, finding y-intercepts, finding asymptotes, horizontal, vertical, slant, all those things to graph. Okay? What we're going to do today is kind of the same thing, but we're not going to deliberately graph it. That's not the goal here. Okay? The goal here is to go through some algebra by hand. That is maybe a little bit quicker than what we've been doing. That is going to provide us with an understanding of where, if we were to graph it, where would that graph be above the x-axis, and maybe where would it be below the x-axis. So we're going to look at inequalities here, but specifically inequalities where your polynomial or your rational function is above or below 0. Okay? That's the easiest thing for us to do in regards to inequalities, whether they be polynomial, whether they be linear, whether they be rational, nonlinear, whatever. The best thing to do for inequalities is to compare them to 0. Because to see where the below the x-axis and above the x-axis is so much easier than anything else. Okay? For instance, we're going to do one here in a moment. Let me just give you a quick visual of what we're going to be tasked with. Okay? If we have the polynomial here. Let's go 2x cubed plus x squared minus 6 is equal to 1. Plus.
Mr. Fay,
Yes.
does the name Pavlov ring a bell?
Yep.
Oh man, that wasn't funny, I guess.
I got it.
Okay. Kind of sad now.
Pavlov dogs. Rang bell. They got hungry. You don't know any of that?
No.
Oh my goodness.
Yeah, Rover hasn't heard of it either.
I got it, Vince. I laughed inside.
That makes me slightly less depressed than my failure of a joke.
Alright, so we're gonna be asked the question of this. When is the red curve above or below the blue one? So let's just say, let's go with above. Where is the red one above the blue one? Okay? So the way to do this is that we graph both of them, and then we find their intersections, because their intersections is where they're equal, right? So then everywhere else would be where they're unequal, and then we just got to figure out where they're, or how they're unequal, which one's above, which one's below. So would you guys agree that if I ask you for these intersection points, let's see here, intersect that and that, I get this point A, which is at -3, -39. From an x value of -3 all the way up to an x value of 2, would you, or sorry, 0.5, would you agree that the red curve is above the blue one?
Yes.
Yeah. Okay. But then after that, after 0.5, they change order, right? Now the red one is underneath the blue one, so the red one would be less than the blue one. But then we get back up here to an x value of 2, and now the red one is above the blue one again, right? So that's kind of what we're doing, is to show the x values that basically from -3 up to 1/2 is the inequality that, or the interval that we're looking for that would satisfy the inequality, where we would say that 2x cubed plus x squared plus 6 is greater than or equal to 13x. And then from 2 to positive infinity, the same thing holds. Okay? That's kind of a pain in the butt with those two functions because of the nature of the blue line. Okay? It would be a lot easier if that blue line was not sloped like that. Okay? it would be a lot easier if I could maybe, because this is inequality, so we've actually got a greater than sign here, and then 13x on the other side, right? Does that make sense to everybody? It would look like this. This is what we're looking at. That's what we'll start with. It would be much easier to move this 13x over here, deal with really a different polynomial, but the results that I get are the same. And comparing it instead of 13x, compare it to 0. So, because we know we should be able to maintain equality if we do the same thing to both sides of the equation, right? So subtract 13x from both sides, and your inequality should still be maintained in the same order. Okay? So I'm going to do that. I'm going to move this 13x to the left-hand side, and then I'm going to make this thing 0. And now the goal is, tell me where that red curve is above the blue one being the x-axis. Is that a lot easier to do? The red one is above between a and b, right? So find what that interval is, which is going to be -3 to 1/2, which is the same thing we just found looking at the other two. And then from c to the right, right? So that would be from 2 to infinity. So it's much easier to look at those two curves than the other two. All right, that's kind of what we're going to do here. Whenever you want to, and this, not just for polynomial inequalities, not just for rational inequalities, not just for linear inequalities, anytime you deal with inequalities, the easiest thing for you to do is to transform them so you can compare it to 0. Make one of your functions 0. So it's the x-axis, and then all you got to do is find out where it's above and below the x-axis. Well, how do I find that it's above and below the x-axis? Where are those cutoff points? What is A considered for my polynomial if it crosses the x-axis? It's a what? I heard it.
Intercept.
It's an x-intercept. So it's a 0 for this thing up here, right? Okay. So it's really easy looking at this thing greater than or equal to 0. We're able to factor this like we've been factoring things to find A, B, and C. Which, if we were looking at the previous one where I had 2x cubed plus x squared plus 6 greater than or equal to 13x, there we have basically a nonlinear system that is really difficult to find those x values of intersection. Okay? But it's a lot easier when we can transform things and deal with zeros instead. Is that okay with everybody? So that's the purpose of why we got to get an equal to 0. I'm not saying it's not doable. I'm not saying that when we look at it this way, that you can't do that. That you can't algebraically find those 3x values of where those two curves intersect. It's just a lot more difficult than looking at the zeros. Okay? And that's just something I would think that maybe you guys want to commit to memory every time you deal with any type of inequality. Compare it to 0. It's just so much easier. So here's what's happening. Like I said, with polynomials, with rational functions, in the past month or so, we've been focusing on how to graph those, right? And we should be able to maybe graph a fourth degree polynomial like we have here. Okay. But the next question is going to be, if the blue curve is where p of x is equal to 4 times x minus 2 times x plus 1 times x minus 0.5 times x plus 2, we then want to say, okay, if that's the blue curve, where is the blue curve greater than 0? Okay? Well, greater than 0, the blue curve greater than 0 would be in all those tan regions, right? Okay? So we would go through, and this is what the procedure that I'm going to show you here in a moment, would go through and find these tan regions without us physically graphing the blue curve. Okay? And if I wanted to see where the blue curve, the p of x, was below 0, less than or equal to 0 maybe, then that's going to be the orange curves, or the orange intervals. Okay? So the process that we go through today, we're going to eliminate having to graph anything to find the solutions to this. But we're going to have infinite solutions. Okay? That's what inequalities incorporate, is a series of infinite solutions. And this is the process for doing that. Okay, now this says for polynomial inequalities, but the steps are extremely similar when we deal with rational inequalities. So there'll be kind of one exception that we have to talk about, but it's really easy. Here's what happens. The first thing, we're going to actually see some examples of this today, but the first thing is to write the inequality so that all your non-zero terms are on one side. Okay? So basically moving everything, I always move everything to the left. Okay? We're going to see that sometimes in rational inequalities, that's a little bit more difficult than maybe in polynomial inequalities. Okay? You then need to make sure that your polynomial or rational function on the left-hand side is in a format in which you can factor it. Okay? So let's say, it's not too bad. Let's say I had like x squared plus 4x is less than or equal to negative 4. Okay? I would bring that 4 over. And now I've got something that I can factor, right? You can factor that x squared plus 4x plus 4. That's what I mean by it's in a form that you can factor. If I had something like this, let's say that I had x, and then x plus 4 is less than or equal to negative 4. Okay? I have to move that 4 over again. Make it look like that. Okay? Now, in order to get this in a form that I can factor, because that's not factored, right? I don't know all the zeros. So what I have to do is I have to actually do the expansion of x squared plus 4x plus 4 less than or equal to 0. Now that's in a format that I can factor, right? Okay. It really becomes an issue. You'll see maybe that a couple times with polynomials, but it really becomes an issue when we have something. I'll just keep it very simple. Let's go like x plus 2 over x minus 3 is greater than or equal to 1. Okay? I'm going to move that 1 over to get my 0 over here. So I have x plus 2 over x minus 3 minus 1 is greater than or equal to 0, right? Now that's not in a form to factor. X plus 2 and x minus 3 may or may not be the actual zeros for this function, because this thing here needs to be combined. We need one fraction over here, one ratio. So how do I add or subtract two fractions? Common denominator. So I'm going to rewrite this thing as x minus 3 over x minus 3. So now this becomes x plus 2 minus x plus 3 over x minus 3 is greater than or equal to 0. That negative needs to be distributed to both things there. So now this gives me, 5 over x minus 3 is greater than or equal to 0. And that's the thing that we would then deal with for the procedure that's about to take place in steps 3, 4, and 5. Okay? Where if I would have looked at this initially, I would have thought maybe negative 2 and positive 3 were zeros, right? But once I do the correct algebra, only positive 3 is the only 0 that exists here. Is that doable? Okay. Those are, I'm not saying every question is that way, because a lot of times they'll start you off with this thing. Okay? But always remember, in mathematics, if the process changes a little bit, can I change a little bit? Can I adapt a little bit when instead of giving me zeros over here, they give me a 1 or a 2 or maybe another rational expression over there, okay? We have to have that prerequisite math to be able to set that up. So what we're looking at is either a p of x greater than or equal to 0 or less than or equal to 0, or just less than or just greater than. And then the other one will be when we just have a p of x divided by a q of x greater than or equal, less than or equal, greater than, or just less than 0. Those are the options that we're looking for, okay? And on that bottom one, it can only be one numerator, one denominator, one ratio over here. So you gotta do that preliminary algebra of condensing common denominators, adding, subtracting fractions, that kind of stuff. Okay. And that's what a lot of algebra 1, algebra 2 kind of help us build those skills so we can do some of this stuff. So here's what we do. We move all the terms to one side. Okay, and that incorporates what we just talked about. It says factor the polynomial. That also kind of incorporates what we talked about got to be able to get it into a format that allows us to factor. Okay. So we do that, and that's another reason why we want 0 over here. If this number is not 0, we can't factor it. Okay. So we factor it down to our irreducible factors and find the zeros of those factors. Okay. The zeros of those factors are really what kind of drives this process and what allows this process to work. So we're going to find the zeros, and we're going to write a number line out. Okay, we draw that number line out. We're going to place the zeros on that number line in order from left to right where they show up. Okay. Step 4 then says you make a table. You're going to use test values to make a table or a diagram for the signs of each factor, and then at the end we're going to figure out how all those factors kind of combine inside my polynomial to provide me either positive or negative numbers inside those specific intervals. Okay. Now that's a vague description of what we're going to do. It's so much easier to see the process, I think. And then once we see the process, we do the process in class. You can kind of compare what we did back to this box of rules, and you see that this box of rules probably makes a little bit more sense after that. Okay. So let's do one, and we'll do that one that kind of started class off with GeoGebra. Let's go. Let's say p of x. Let's not write that one. Let's say we're going to square 2x cubed plus x squared minus 6 is greater than or equal to 13x plus 6. So x cubed plus x squared plus 6. Okay. So we move all terms to one side. Move everything to one side. Get everything equal to 0. So it gives me 2x cubed plus x squared plus 6 minus 13x greater than or equal to 0. Okay? So now it's in a format in which we can factor. Now here's the thing. You have all different types of ways of factoring. You have, here I see it's a cubic, so I have potentially factor by grouping. I could maybe look at the first 2 factors and see that I can take out an x squared, right? And I can look at the last 2 and see that I can't really take anything out, take a 1 out, but that's not going to give me the same things in the parentheses, right? When I do the factor by grouping. So factor by grouping doesn't work here. And with something larger than x squared, usually if factor by grouping doesn't work, your next option is p over q, right? Okay, which may or may not be too difficult. You write all your, this one, it's not too bad because and I guess actually we can't do p over q because these are not integer coefficients. Because my plus 0, they are integer coefficients plus 0, but factors of 0 really aren't. P over q, 0 over 1, 0 over 2 doesn't give me anything useful here. I need to do p over q. Actually, I'm sorry. Never mind. What did I do wrong? What was I talking about? I do have a constant component, right? I didn't put this in descending order, so. Now my p-values are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, right? My q's are plus or minus 1, plus or minus 2. So you would go through that, okay? Now my hopes are that this is the way you guys start thinking. We've already done the p over q stuff, and you guys have been proficient on tests and quizzes on doing that, okay? Do not waste your time doing a lot of p over q stuff right now as preliminary math to get somewhere else. Does that make sense? Eventually, maybe you have to, but you're always going to have your calculator. You're always going to have your computer. You're always going to be able to maybe use some technology to help you find the zero so that you're not going through and testing maybe 5, 6, 7 possible p over q values to factor these things. So be intelligent about the things that you have at your disposal to get this thing broken down to its factors. Okay. Maybe one thing you could do is graph this in GeoGebra, graph it on your TIE 384, and go through and find the x-intercepts, okay? And you're going to find out, I think, that one of those x-intercepts is like 2, okay? So x minus 2, so an x-intercept would have been 2. It gives me the factor x minus 2, so I know maybe through synthetic division that 2 would have worked. And you can then divide this through synthetic division, so maybe, I'll just do this real quick. Right, 2 there, 2, 1, negative 13, 6. Bring my 2 down, gives me 4, 5, 10, negative 3, negative 6, gives me a 0. Now you have 2x squared plus 5x minus 3. And now you could do the a times c method with that quadratic to get these other 2 components. Does that make sense? Okay. So that's, algebra right now that I don't want to focus on because we've been doing that for a while. But that would be the first test. Take all your tools that you have in order to get this thing factored down to x minus 2, 2x minus 1, x plus 3. Okay. On tests and quizzes, what I will do, I'm not going to, maybe only take home one because you're going to have somewhat unlimited time on that. Give you maybe one of these where you do have to go through all that P over Q stuff. Now, some people might go through all the P over Q, some people might use computer, calculator, whatever, I don't care. But like in an in-class test or quiz, I can't give you this and tell you, don't use your calculator, don't use your computer, do the P over Q stuff, spend 20 minutes on doing that, and then try to finish answering the problem, and then 4 other problems. Does that make sense? We're confined with time. So maybe on a test or quiz, maybe I give you that 2 is a 0. And then you have the ability to quickly divide this thing out to get that 2x squared, I think it was plus 5x minus 3 or something like that. Get that quadratic. And then you can factor that quadratic to this. Or maybe I just already give it to you in factored form. Okay? But that's the first step you have to do, is be able to get these polynomials completely factored using any tool that we've talked about, Algebra 1, Algebra 2, first part of this class. That's kind of why those courses are structured the way they are in regards to content, is so we can move on in this class. Okay, Algebra 2 is a lot of factoring, right? Mm-hmm. What we've done so far has been a lot of factoring, right? And so we can use those skills to learn things about inequalities, to learn things about other types of functions and stuff like that. Okay, so here's what you do then. Once you've done this, you've done all the hard stuff. Okay, the factoring is the most complicated part of these. The next thing you do is you create your number line. Okay, so we're in the process here of steps 3 and 4. Okay, I do 3 and 4 together. Okay, so you make your number line, and on your number line you're going to put these zeros down. Okay, so x minus 2 provides a 0 of 2. 2x minus 1 provides a 0 of what, 1/2? And x plus 3 provides a 0 of -3. Okay? The spacing of them, the scaling, doesn't have to be accurate, doesn't have to be, obviously there's a shorter gap between these two than there is between these two, right? If you maintain it, that's fine. If you don't, doesn't matter. Okay? This is just to organize our information. Just to keep things organized, I always put those vertical lines in there. If you want to, you can, you don't have to. But I think it's a good idea to do that. Okay. Here's the idea, guys. This is what we're gonna do. When we break up the number line into those intervals, we know that when we choose, say, -3 for a value, so give me -5 here, so give me -7 there, and so give me 0 there, right? When I multiply those 3 numbers together, what do you get? You get 0. Okay. Same thing for a half, right? A half will give me, -1.5 here. It'll give me 0 here. It'll give me 3.5 here, right? I multiply those together. What do I get? 0. When I plug in 2, I get 0. I get 3, and I get 5, right? Product gives me 0, right? Okay. So the intermediate value theorem says that this graph, if those are the places that you get 0, to the left of those, you might have a positive or negative y value. to the right of them, you might have a positive or negative y value. Does that make sense? Okay. And what that means to us then is that if I've found the zeros, and then to the left of this thing, it's positive, then I know that we satisfied this inequality. Maybe if to the left of it's negative, but to the right of it's positive, then in this region, I've satisfied this inequality. Does that kind of make sense? Okay. But each one of these things, dependent on what x is, each one of those things is a number, right? Each one of those factors provides just a concrete value. And we're going to that expression, that equation tells us to multiply them all together. Okay? Well, if I have an odd amount of negative numbers up there, what is my total going to be? If this was a positive number and that one was negative and that one was positive, what would the total be? You have a positive number times a negative times a positive. What does that provide you?
Negative.
Give you a negative, right? Okay. Not what we're looking for, correct? But what if I had something like this? What if this ended up being negative, a negative, and that was a positive? What kind of number would that be?
Positive.
Positive. And that's greater than 0, right? So when I can determine when maybe these relationships exist where two of these are negative, and this one's positive, or one of them's positive, then I'd be above 0. Or if they're all positive, would I still be above 0? So that's what we're trying to figure out. That's what this table is going to do, is find all the places, all the different arrangements where this could be positive, that could be positive, that could be negative. Or this could be negative, 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 or negative, negative, positive, negative, positive, negative. Does that make sense? And then kind of collect those and see, okay, which ones provide me the entire polynomial to be positive, and which ones provide me where the entire polynomial is negative. So this is how you do this. You take these factors and you write them over here as a list. Over here, x minus 2, we're going to 2x minus 1, and then x plus 3. Okay? And we write those factors down because those are the individual values, right? When I know what x is, those numbers are what work together to either provide me a positive or a negative number. The last thing you're going to write down here, I like to write either total or just p of x, doesn't really matter. A lot of times you'll see like people online that do this, they'll write like x minus 2 times 2x minus 1 times x plus 3. They'll write the whole thing here. Or they'll write the original 2x cubed plus x squared plus 6 minus 13x. I think that's a little bit more work in writing than we want. Just write total here, referring then that total means this stuff here on the left. So now we just start choosing values. We know that negative 3, 1/2, and 2 are going to provide me 0. So let's choose a number to the left of negative 3. So what's a number over here to the left of negative 3 that you could choose? Negative 5. Perfectly fine. There's an endless number of correct answers that you could use there. So I choose negative 5. So what's negative 5 minus 2? Negative 7. Now, I only care about the sign. If you want to put the number in, you can. Okay? But negative 7 times negative 5 times negative 11, whatever that is, it's still going to be negative, right? No matter how large it is, it's still negative. And that's what I'm interested in. Okay? So, negative 5 minus 2 is negative 7, so I get a negative quantity there. Negative 5 plugged in here should give me what? Negative 11. And then negative 5 plugged in here should give me negative 2. Okay? So we had 7, 11, so that's what? Negative 77 times in negative 2, right? Okay? It's a pretty large number, right? Okay? I don't care that it's, what is it, negative 154? I don't care that it's negative 154. I care that it's negative. Okay? Because if it's negative 1, or if it's negative 154, or if it's negative 0.3, or if it's negative 100 million, is it still less than 0? Yes. Okay, and that's all I care about. Is it below or above 0 in this case? So my total here is negative in any x value that you choose over here. And the idea is, if I chose negative 5, or chose negative 6, negative 7, okay, if I chose negative 7, that negative 5 that we used initially gave me a negative 7 here. If I choose negative, let's say negative 8 instead, that's going to be just a bigger negative number, right? That's just going to be a bigger negative number. That's just going to be a bigger negative number. That's just going to be a bigger negative number, right? But yet still negative. So it doesn't matter which numbers you choose over here. They're all going to have the same relationship. Now you're going to choose a number in between here. Okay? Now, between -3 and 1/2, what's a really good number to substitute? 0. So whenever you get the option to use 0, use it. Okay? You don't have to. You could use -2, you could use -1, you could use -2.9. But use things that are maybe intelligent. So if I choose choose 0, it gives me a negative there for that negative x minus 2, right? If I choose 0 here, what's that going to give me? -1, so negative. And if I plug 0 into this one, what's that give me? Positive, right? So what we just figured out is that we got a negative times a positive. If I multiply those together, what is that always going to produce me? Positive number. So my total then, right there, is positive. Now I gotta go find a number between 1/2 and 2. What's a really good number between 1/2 and 2? 1. So plug 1 in. What do I get here for this first factor? -1. What do I get here? +1. And what do I get here? +4. So I get a negative times a positive times a positive. And a negative times a positive times a positive is a negative. And now choose a number to the right of 2. Doesn't matter how big. 5. So 5 minus 2 is 3. So positive. Positive. Positive, right? So a positive times a positive times a positive is a positive. Okay? Now, we have, 16 signs there, right? But these 12 are the ones that, in combination with one another, provide me the totals. And those totals are the ones that we're interested in, okay? So when I look at my totals, okay, remember this is what I'm referring to as the total, or P of x, okay? When is that thing greater than or equal to 0? Or greater than or equal to 0, another way of saying that is 0 or positive numbers, right? Well, is it obvious then that positive numbers occurred between -3 and 1/2? Because that was the total is positive here. And then total is positive also at values that are greater than 2. Okay? So I always kind of graphically go back in and find on my number line. That's usually the way I do it, kind of like that, so you can see the distinction between the number line and my solutions. Graph it on there, okay, and then I want to convert that into interval notation. So writing these green values down. The first one would be -3. The last one would be 1/2 in that green interval, right? Now, we got to pay attention to equality here. If it's equal, that means you could have used -3, right? It means you could have used 1/2. So I'll put a bracket there and a bracket there. I'm going to skip these values because those were negative. They're not what I want. And I'll get to 2. I'll include 2. And then I can go all the way to infinity. Okay? And that set of solutions is exactly the same set of solutions in which, if we were to come back to the original problem, when we were asked where that cubic is above or equal to that line, okay, it would occur in those two intervals. Okay? The only thing you got to pay attention to is that changes periodically is whether they give it to you as greater than or equal to or just greater than. A lot of times they'll, just like anything else, I guess, in this course or any math courses, that they get you in a habit. Say, okay, do greater than or equal to on 3, 4, 5 questions. And then the next question is just a greater than sign. If it's just a greater than sign, okay, choosing -3 would actually put a 0 here, right? Is 0 greater than 0? No. So what would I need to do on -3 here? I need to open that dot up, right? Same thing here on 1/2 and 2, which would change these to parentheses, correct? Okay. So just be leery of that. If you know you're doing everything right, but you're typing something in with brackets and it's kicking back the wrong answer, sit and think, am I looking at the right inequality? Okay. If it's greater than or just less than, they need to be open dots. And if it's equality, they gotta be closed limits. Okay. Let's do one, and we're gonna be kind of crunched for time here, but I'm gonna give you an idea of how to do this with rational functions, and really the only difference that occurs with rational functions. If we were to go through here and look at these rules, these guidelines for a rational inequality, they're going to be the same. They're pretty much the same exact thing as what we just did. The only exception is division by zero. So we always got to remind ourselves that we cannot divide by zero. So when we set up our number line, there's going to be one additional step that we use for that. Okay. Same idea though as before. I got 1 minus 2x over x squared minus 2x minus 3. Where is that greater than or equal to 1? Okay. So we got some function here. Probably looks, something maybe like this. Okay, just guessing here. Maybe it looks something like that. We've been dealing with a lot of stuff like that, right? And now we're interested in where is that thing above 1. Well, to find those points of intersection there and there is going to be difficult. Okay? So let's not look at that. Let's transform this thing so that instead of looking at comparing that line, let's compare to that line. Because if I can compare to that line of y equals 0, things are going to be really easy. Okay? It just basically breaks down to factoring. So I need to take that 1 that's on the right-hand side and move it to the left. Okay? So what you end up with is 1 minus 2x over x squared minus, is it minus 2x minus 3? Yeah. Minus 2x minus 3. Okay? Minus then 1 is greater than or equal to 0. Okay? Well, there you've got two fractions, right? How do you add two fractions? Common denominator, right? What's common denominator going to be here? Yeah, so I'm going to have 1 minus 2x over x squared minus 2x minus 3 minus x squared minus 2x minus 3 over x squared minus 2x minus 3. So I rewrite that negative 1 so that it has a common denominator, right? Greater than or equal to 0. Now I can do the subtraction, but this subtraction, this is where people mess up all the time. It's minus that entire thing, right? So it's going to be 1 minus 2x minus x squared plus 2x plus 3 all over x squared minus 2x minus 3 greater than or equal to 0. Now the top, minus 2x's cancel out with positive 2x, and you have now, 4 minus x squared? So 4 minus x squared all over x squared minus 2x minus 3 is greater than or equal to 0. That's what we're going to factor. So what you're seeing there, those steps of being able to add ratios is, a lot of stuff that we did in Algebra 2, and we did that in maybe Chapter 1 and even the prerequisite information that we covered a little bit before we really got into the textbook of this course. Okay. Now I'm going to factor this. This is the difference of perfect squares. So we get 2 minus x, 2 plus x. The bottom gives me, x minus 3 and x plus 1. And we're interested in when that is greater than or equal to 0. So now we factor this thing completely, right? The only thing we got to worry about here is when we create our number line. We're going to put in all these zeros. So we have a 0 of, positive 2. We have a 0 of negative 2. And now when I get to these zeros of 3 and negative 1, perfectly fine, write 3, write negative 1, but can they ever be solutions? Can I ever choose 3 and plug 3 into this function? No, because it'll give me a 0 on the bottom, right? It'll be some number divided by 0, and you can't do that. So you just need to remind yourself that those things got to be open dots. Okay? when they become part of our intervals for our answers, if they are intervals for our answers, we need to make sure we kick those values out. So those are open dots. Otherwise, the process is the same. Write all my factors over here. 2 minus x, 2 plus x, x minus 3, x plus 1, and then my total. Okay, so just kind of quickly going through this. If I choose like -5, 2 minus -5 would be positive 7, right? Okay. 2 plus -5 would give me a negative. -5 minus 3 would be a negative. -5 plus 1 would be a negative, right? You have 3 negatives here, correct? And that's really all I'm interested in, because we know by Algebra 1 information, a product of product of odd negatives gives me a, if I have odd factors that are negative, that product is going to be negative, right? Okay. So 3 odd negative factors, so my total is negative, right? Now here it kind of stinks because you have to choose a fraction. So -1.5. Okay, -1.5. 2 minus -1.5 is going to be positive, right? 2 plus -1.5 is going to be positive. -1.5 minus 3 is going to be negative. And -1.5 plus 1 is going to be negative. So what's that going to be as a total? Positive. 0. So it gives me 2, which is positive. It gives me positive, negative, positive. So that total is negative. I'll keep going through here to show you the entire solution. I'll catch it on video and I'll post that. There is an assignment on Web Science, not due tomorrow, but it's something that you can start looking at, start working with. We'll go from there tomorrow.
You want me to end this for you?
No, not yet.
Just to finish it.
Yeah, sounds good. Hey, you know where Paris Lawrence is right now?
Harris?
Yeah, I need her for a political club interview with Natalie Crow.
Not quite sure. Probably no year, but. Oh, right.
I have to interview Alexis.
Huh? Work at Happy Days? Oh, I'm not working at Captain D's. Question, I work at Captain D's.
You do what you want, man.
You were getting close to no.
You will gain money. Dude, you work for $8.
Yeah, I know, but I don't know. I don't know, Jarrett. I'm not cut out for that kind of work. I'm sensitive to the